You don't hear any audio right now?
No, now we hear you, but if you're playing a video, we don't hear the audio from the video, I guess.
Okay. I can.
Maybe
Okay.
just
I
go
can
manuals.
Yeah. So hello everyone. This is Ahmed Hamada presenting implementation of partial average Navier-Stokes equation, turbulent closure model in OpenFOAM. This work was done with cooperation of Lubna Maraga under supervision of Professor Saraj Al-Maji and Professor Miriam Forth. The outline of this presentation starts with motivation, then we go through introduction and objectives will be stated. Next, the governing equation will be discussed, and we will go through the library implementation in OpenFOAM, and we will discuss our result cases, and finally, the conclusion will be presented. The RANS methodology is a computationally efficient but limited in capturing the full range of flow physics, coherent turbulence, due to its one-point closure approach. DNS and LAS technique provide accurate computations, but may be excessive and computationally burdensome for applications that only require coherent flow around complicated aerospace and ocean engineering application. So a quick comparison between neurons, LAS, and DNS. You can see that neurons only focus on the mean features, while LAS you can see the large and the medium scales of turbulence. DNS you can see the whole scales of turbulence, large, medium, and small. So it's always a compromise between the accuracy and the computational power. So our question here, which level of complexity should be selected? Turbulence rely over a wide range of scales. The large scale, which is production happens and cannot be modeled because it's depending on the shape of the geometry. The medium scale, it's the inertial range. It's difficult to be modeled, but it can be. The dissipation, happens in the smallest scale, and this is the easiest one to be modeled. So any turbulent quantity can be decomposed into three parameters: the mean field, where the whole scales, domain of scales are averaged, and the coherent structure that happens over the large and medium scales, and the stochastic turbulence that happens in the smaller scales. If we combine the stochastic and coherent, we get the fluctuation field, and when we focus only on the mean field, we get the RANS by modeling the whole range of turbulence. If we resolve more large and medium scales and only models the small one, we get the LAS. When we resolve the whole range of scales, we get the RANS ones. Another decomposition can be happened for any turbulent quantity by using a filter. The filter means that I enable some scales to be resolved and some other scales to be modeled. This gives me the filtered equations, and to composing the turbulent quantity into two parts: filter field and residual field. The filter field happens by bands. So the bands divide the domain into residual and resolved and unresolved. A quick example of bands: if we have a signal, if we consider a filter value of 1, so we are modeling everything, we only concern about the mean, and put everything in the residual. The residual here becomes the fluctuation, and this case is the RANS one. By decreasing the filter, we are enabling more resolving area to happen, and reaching to filter value of 0, where all the scales are resolved and there is nothing in the residual, and this case is the DNS case. So the implementation of bands in many applications using OpenFOAM has been widely conducted. However, the implementation was achieved by changing the closure coefficient values of the used turbulent model in OpenFOAM input file, the turbulent property file, which correspond to a certain resolved kinetic energy and resolved dissipation filter. So our objective to build a bands turbulent modeling library in OpenFOAM, in which the evolution equation of the turbulent kinetic energy and dissipation in K omega, K epsilon, and K omega SST models are adjusted with just defining the bands filter to provide simplicity for OpenFOAM user to implement the bands turbulent modeling in their simulation, obtaining more accurate results than RANS. So the governing equation, the filtered Navier-Stokes equation for incompressible flow looks like this. It's very similar to the RANS one, except we switch between the mean parameter with a filter parameter. The tau ij is no longer called a resist stress; it is the generalized central moment, and this is the equation for multi-phase flow because we will go through two kinds of problems in validation and verification. The second one is multi-phase. The turbulent modeling, the generalized central moment is it's defined as multiplication and sum of bunch of filtered and residual quantities, and it can be modeled by Bose-Naski approximation using negative 2/3 Ku, etc. The bands filter Kfk and F epsilon is the ratio between the unresolved part to the whole domain, and F omega can be defined based on F epsilon and Fk based on the relation between omega and k and epsilon. The evolution equation for the occlusion model here is developed for a constant Fk over the whole domain. And this can be easily done to generate these governing equations of illusion equation for k. You can see the edit happens in the transport part. There is F omega over Fk for k omega and F epsilon over Fk square for k epsilon. And it's affecting the dissipation equations in the two parts. The first one in the sink of the dissipation, the second term of here or here. And it's affecting also the transport of the dissipation, as you see here. And for k omega SST, it's affecting also the cross diffusion term by this factor. So what's the process for implementing bands in OpenFOAM? Firstly, we'll examine the existing turbulent model library structure in OpenFOAM. We can see that our model is generalized in two parts, the RAS one and the base one. So the next one is to define this modules and generate our band subroutines and its own file dependency. This has happened. Then we go through defining the bands filter in our code. This has happened by declaring the filter values in the H file and give it a default value of 1 if not given. And of course, if it's given, the OpenFOAM will use the given value by read if present. And then we will implement the bands model by adjusting the transport equations, our transport part, sorry, in the evolution equations, as you can see by these factors, and adjusting the sink of the dissipation, as you can see here, and adjusting the cross diffusion term too. Then we will modify the makefile to add the bands to the turbulent selection table and include bands to the turbulent models library. Next is to integrate the bands into different flow subroutines. We have incompressible and compressible, and this will cover the multiphase too by defining bands model in the incompressible transport models and include bands model and calling its name. I just call it by adding bands at the end, and we can do it for compressible flow again. But in compressible flow, we need to define the bands model in the make.h. Next, as a final step, is to compile and verify, and likely this is one very well for us. So verification for that. A verification process was carried out to establish confidence in the developed bands technique in OpenFOAM and its correct functioning before proceeding for further computational analysis and discussion. This process involving comparing the result of two turbulent model simulation. One used RAS model and the other employs the bands model with unity filter. So we are using RANS simulation for both RAS and bands. And another comparison was made between a RAS simulation in which turbulent model coefficient was manually adjusted in the input file, the turbulent property. So we are adjusting the coefficient there with a certain filter of Fk upon 2, and the second one is band simulation by just declaring the filter values of 0.2. This is done for a simple problem, turbulent flow around square cylinder. This is looks like the mesh. It's very basic mesh, but this is just used for sake of verification, not for solving the problem itself. And this is the boundary that we used, and showing the result. As you can see, the RAS one of and the bands with FK and F epsilon of 1. So this is round simulation. It's identically the same. There is no change here in the first line and in the third line for CL, CD, and CL over CD in the frequency domain to show the frequency, the dominant frequency, and also the power spectrum. But when we go for FK of 0.2, we can see that it's different between the bronze one and bands one. The reason is that when we define the coefficient, turbulent coefficient in the rounds one, adjusting it manually, of course we use a round off. We cannot type the whole 16 digit of the coefficient, and this causes a deviation between the actual running bands by just declaring the coefficient and just declaring the filter value, sorry, and the rounds one by adjusting the coefficient manually. So comparing it in numbers, as you can see, the Stroll number for FK, CL, CD, the separation point behind the attachment point of the separation bubble behind the square cylinder, everything almost the same, even the computational time for FK equal 1. For FK equal 2, the deviation is almost quiet, as I said, because of adjusting the coefficient of fronts manually. And you can see that, of course, the bands one will take more time than the rounds one. This is makes sense because we are resolving more scales, so we are consuming more computational time. But all other numbers almost the same. This means the verification went very well. Then we go for the simulation by comparing it with DNS. We tested two filter value, FK of 1 and FK of 5. You can see that for DNS separation point, the reattachment of separation bubble behind the square cylinder is almost at near 1, and here it's very far. But when we use FK, it became very good. And also for vortex shedding, it's only appearing in rounds because this is averaging all the frequencies to present only the dominant frequency, which is vortex shedding. But the reality, there is some vortex stretching. This happens in DNS, and some of the vortex stretching is appeared in FK 0.5. Going for numerics, some numbers. As you can see, this is a literature, the DNS one, and the values of F1 and 0.5. You can see the error for the separation point decreased from 28% to 5%, and for strong number from 10% to 1.9. There is a quite deviation in the CD mean, but this can be solved by taking more time, more turbulent time, so more turbulent simulation time, or adjusting the mesh near to the square cylinder. So bands proved its case for incompressible flow. Let's go for another case of multi-phase flow. We have a hull fixed at a certain trim angle, and there is a current speed moving over it of water. This problem called high-speed craft running in a calm water. So this is the boundary condition shown in the figure, and we run it at a speed of 17.5 knots, and we measure the resistance over the weight of the hull, resistance delta, and we can just get it by getting the forces and apply it to this equation. Firstly, we did a mesh independent test, of course, medium and fine. As you can see, the result is converging after the medium, but we stick to the fine for our simulations. The error decreased, reaching to, with respect to mesh 3, the finest one, to 2% and 0.19. And when we use Selig et al. And the Richardson extrapolation technique, we find the fine is the error in it 2.5 and 0.1056. So then we go for bands. As you can see, by comparing our result with experimental data, the error decreased from 50% to 2.7% when we switch from runs to bands with FK of 0.2. Also, this was very confident in our results that the literature said that when we use runs in this such kind of simulation, we have some yellow part here showing that there is some numerical error near to the keel. That means there's some error. But this error is not in the reality in the experiment, and this is numerical error. When we use bands one, it became all red. There is no yellow anymore. And this means the bands managed to capture the physics properly. So our conclusion, the results demonstrate that the bands model can capture the important feature of turbulent flow with reasonable accuracy and computational efficiency, making it promising tool for a wide range of safety application. Overall, the implementation of bands model in OpenFOAM provide a valuable addition to existing turbulent model. Capabilities of this wide use safety software package, OpenFOAM of course, avoiding user floats in editing the turbulent input file, and spreading the knowledge of bands technique among the OpenFOAM community. So our conclusion in very short message, we can use bands by just defining the Fk and F omega or F epsilon for K epsilon technique. Just a few lines we need to define. And that's all for now. Thank you for your attention. If you have any question, I am very welcome to have it in Q&A or send me email. Thank you.
Hi. So this is Tariq here. So I'm going to present some simulations on a convective boundary layer, a barotropic convective boundary layer. I'm a PhD candidate. I started my PhD a few months ago. So these are very preliminary results. And I'm doing a PhD in UPC Barcelona. So this is the outline of my presentation. And so let's start with a quick introduction of the atmospheric boundary layer. So this is the boundary layer, the atmospheric boundary layer, the lowermost part of the atmosphere. So all the human activities and influence the turbulence generated in the atmospheric boundary layer, mainly by rising thermals also during daytime and in the stable condition, so at night at the low level jet. So as everything, pretty much everything needed for human civilization is in the atmospheric boundary layer. So understanding the turbulence properties of atmospheric boundary layer is of paramount importance. So the motivation of this work is to investigate alias. But before that, as you know, that ABL is a very complex and multi-scale nonlinear flow. So it needs to understand its inherent coherent structures. We need high fidelity methods, especially at least alias. As you can see in the figure, the daytime convective boundary layer has the thermals moving up along with humidity, and that also interacts with the airflow. And the bottom picture, which is a DNS result showing the humidity, the green colored one going up and interacting with the dry air in the free atmosphere. So there are lots of scales from tiny scales to larger scales, and also time scales. And all these are important to capture in order to understand the coherent structures inside the ABL. And however, that as DNS is really expensive, until now the DNS of atmospheric boundary layer investigations are limited within the Reynolds number order of 10 to the power 4, and limited to idealized configurations, not the real life ones. So in general, the alias and RANs are preferred by academia and also in the industries. However, DNS are still useful because as the ABL turbulence properties become Reynolds number independent after 10 to the power 4 Reynolds number is reached. So thus the turbulence property is captured by the DNS in the simplified configuration is still valuable for development and validation of numerical models, especially for the alias. So although alias have been contacted for ABL for since 1980s, but until now, stable atmospheric boundary layer is still the challenge, especially because there are mainly 2 points. The larger energetic eddies in the stable ABL is very small, approximately 1 meter, whereas in typical ABL alias of ABL, people generally use 10 meters. So it is needs very fine resolution, and also required a large computational domain. There's some there's some features of stable ABL, particularly spatial intermittency during turbulent collapse. So what happens is that in the stable ABL, the turbulence laminarizes, and it comes back again. So it happens especially, as you can see in the DNS simulation result at the right side figure. So in the whole domain, there are some turbulent patches along with some laminar part. But if the computational domain is not large enough, this phenomena is not captured. Rather, instead, they predict temporal intermittency, meaning in the whole domain they predict they predict turbulence, and it is gone again after some time, and then the whole domain has a laminar flow. But in reality, it is spatial intermittency, meaning the turbulence and laminar part, they coexist. And if the domain is not large enough, then it is very difficult to obtain this feature. So to address this challenge, I first started aiming with well-resolved alias. And the aim is to capture spatial intermittency, and also, so the idea is to do a atmospheric boundary layer with unstable and also a mixture of stable and unstable part. So the stable part will have the spatial intermittency during turbulence collapse. That feature need to be captured. And as there will be some interaction in the entrainment zone between unstable and stable layer, that needs to be captured as well. And obviously, it should be in moderate Reynolds number. To simplify the case, it should be on flat and a smooth surface, not on rough surface to begin with. And so the chosen configuration is this one, as you can see in the figure. It is a daytime convective boundary layer, a barotropic convective boundary layer, meaning the barotropic conditions, meaning the wind strength is a constant with height. As you can see, it is constant in the free atmosphere. So here we have at the bottom, we have the convective boundary layer, which grows into a linearly stratified stable ABL in the top. So we have the entrainment dynamics in between them, and there's a stable ABL where it is important to capture the spatial intermittency. And this configuration represents a midday condition over land. And this DNS work is mainly governed by 5 control parameters. You know, the nu and kappa. So, and there are 2 more especially. The first one is B naught, which is a constant and homogeneous surface buoyancy flux, and N naught is representing the buoyancy gradient. So to put it into perspective, we have stable and highly stable ABL. So when the N naught value is really high, as you can see, the virtual potential temperature that is representing really high ABL, and at the right hand side we have temperature profile only, that is straight, which is the highly stable. And on the contrary, stable ABL virtual potential temperature is really going directly almost upward. And so these are the difference are stable and highly stable, represented by the N naught. And here in our case, we are considering the highly stable part. I am not sure if I chose the correct one, but I thought to begin with the highly stable part. And in the case setup, as it has heat involved, so I chose beyond Bosonic simple foam, and schemes are first order. The boundary conditions has this ATM turbulent heat flux temperature with the general daytime heat flux from the earth. And it is a 2D setup as we are doing wall resolved, although it is a coherently 3D flow. But as we are doing wall resolved, we wanted to begin with 2D to reduce the computational power and see what we get at the beginning. And these are the boundary condition applied for the other parameters. And here are the initial condition for buoyancy and velocity. And these are applied through internal field code stream. And as I'm yet to learn how to implement humidity in OpenFOAM, so I'm going with dry condition, meaning there's no humidity, only dry air. And the grid, it is considered 4.3 into 5.85 kilometer domain. So 4.3 is in the x-axis and in the height is 5.85. And we have this number of cells in the x and y axis, and almost 250 cells in total. And dx is 5 meter and delta y is at the surface, as we are trying to do wall resolve. So we really wanted to catch y plus equals 1. And so at the surface, it is 685 millimeter delta y, and it ends with almost 28 meter at the top. And the results, so we have here the at 1620 seconds, which is almost a half hour, we can see the thermal plumes that is coming from the earth surface, and there's this u x component of the u velocity. And as we chose the velocity is u equals 1.8, it is pretty much maintained in the free atmosphere, and there's some as there's the boundary layer at the bottom, so we have this gradual increment. However, when this is the DNS result, so as we go with time, as the convective boundary layer, it should have u value equal to it should come into a steady state, the mean value, because it is a convective boundary layer, so everything is mixing up, and adding everything, it should give a constant value. So so it is, as I thought at the beginning, maybe it is approaching there, but when after some time it showed some high velocity in the at the bottom around 100 meter, 500 meter, and eventually it collapsed, and the result became really bad, and it got stable into a totally unphysical fashion. So we have this pattern now, where the ux value is really high, and then it goes to the left, and it should not be happening. What should happen is it should linearize. It should get constant value throughout the domain. And if we consider the temperature profile, so we have that the plumes coming, and it is increasing, but when in the final time step, it is really messing it up, and really unrealistic result. So this is what we have. We are stuck at this point. Now we're investigating what steps to take next. And our thought is to fix the problem by analyzing the RANS investigation and run with a second order scheme from this time step to see if it goes correctly, and extend to 3D domain, because currently it is a 3D problem, and solving in 2D makes are prone to error. And in future work, we are the aim is to extend towards wall modeled alias, and then investigate it into for small rough surfaces, heterogeneous surfaces, and possibly to complex terrain for higher Reynolds number. So that's pretty much everything, and these are my websites, and you can find me in LinkedIn and ResearchGate on this name. So any questions and comments? For as I'm a new PhD student, your comments are really appreciated.
Okay, thank you very much, Tariq. Also, thank you for being pretty fast, but unfortunately we're still late, so we'll have to take the questions in the chat, okay? Thank you very much for your talk. And we move on to our last speaker.